Hey there, folks. Welcome to a new video series we have here on the channel. This is Weather 101. I'm Geology Professor Shawn Willsey, and I'm joined by our course instructor. Ben Papandrea is the lead meteorologist at the Weather Company. He's also taught college courses in meteorology before, and we're going to, in this series, go through a number of lessons where we kind of start with the foundation of how the weather works and the basics of the atmosphere and such, and then kind of build as we get into other topics like severe weather. And what's beautiful about this is this affects everyone, no matter where you are. Just some basic understanding of weather and how it works can be really beneficial just as a citizen of this planet. So Ben, thanks for taking time with us today. And yeah, go ahead and introduce our topic and let's get started.
Okay. All right. Thanks, Sean. So we're going to talk about like the structure of the atmosphere. So just think of this as intro to the atmosphere. So when you learn meteorology, you need a foundation, right? So we can't go right into talking about the super interesting things that you probably want to hear. Like I want to hear about blizzards. I want to hear about tornadoes. I want to hear about hurricanes. When you have this kind of base level knowledge, you'll see how these things become important later on. And when you get deeper in to talking about the super interesting topics that everyone wants to talk, you'll go, oh, I kind of remember that's how that works all the way from the beginning, right? So I think that you're going to find some of this pretty interesting. And the first image here is kind of a sideways view of the Earth, and you can actually see the atmosphere glowing here, right? And of course, beyond that, in that black is space. And just want you to kind of think deep about this for a second. Look how thin that is, right? We have this really thin layer of air that's connected to the Earth. So let's kind of start with the most basic science nerd, let's call it, definition of the atmosphere. It's a envelope of gas, gaseous envelope, gravitationally bound to a celestial body. What does that mean? It means air that's being held down by gravity.
Right, but it can still move around freely on its own, but it just is kept close to the Earth. Is that right?
That's right. So what this means is that the Earth is not the only body that has an atmosphere, right? So Venus has an atmosphere, Mars has an atmosphere, and hopefully at some point we'll get to talk about that because Earth's not the only place that has an atmosphere, and it's not the only planet that has weather too, right? So when we talk about the Earth's atmosphere, we get to talk about the makeup of the atmosphere, what gases are in there. So these are the primary gases in the atmosphere. Now we'll get to the structure of the atmosphere and the layers of it and stuff like that. But the top gas is nitrogen, 78%. And then oxygen at 21%. You say, argon, I've never heard of that. That's below 1%. Now this usually gets everyone carbon dioxide, 0.04%.
Yeah,
And
small.
oftentimes people will, well, wait a minute, that's really low, right? You hear about climate change and you think that that number should be really high, right, Sean? Like you feel like that should be.
Yeah, it should be more of a significant component of the atmosphere since it seems to matter so much in regulating temperatures.
Yeah, and this is sort of like one of those, like it's the dose that creates the poison, or
Yeah.
there's a lot of sayings around that. And like I think percentages, like let me just I always used to love doing this with my students, is just let's say if we had this is a cup, right? And then here's a bigger cup. All right, let's fill this cup. Let's fill this cup. All right. This cup is filled halfway. This cup is filled halfway. But that fraction doesn't tell you how much is in it, right?
Yeah, the
They're both,
quantity, right.
that's right. They're both at 50%. So we have to look at this in sort of a big picture way of that 0.04% carbon dioxide plays a significant role, even though it's only in that tiny fraction.
Right. And
And
would the sorry to ask a quick question, like would the density of those gases, because the atmosphere is like a thick layer, and I know we're going to get to that, but is the carbon dioxide maybe more concentrated at the bottom since it's probably heavier than those other things?
so we and when we get to this, you'll see, so the lower part of the atmosphere, we consider it well mixed, meaning that the gases are distributed evenly.
Okay.
Not until we leave the bottom of the atmosphere where weather occurs that the gases can become more what we call stratified, and they may be like more or less layered. But the lower atmosphere is well mixed. So if you're on top of Mount Everest versus at the Earth's surface, you're going to measure the same percentage of carbon dioxide as a constituent of all the gases, right? Yeah, and let me go back here for a second. And then water vapor, you see 0 to 4%, right? It could be really dry. So water vapor is just water gas. So could be almost nothing if you're in the deep desert, or it could be as much as 4% if you're in a tropical area. And well, how can it, like the other percentages just change a little bit based upon, if there's more water vapor, then the other percentages, nitrogen, oxygen, are going to vary a little bit too, right? It's gonna change based upon how much water vapor is in there. And you're gonna come to see, and I'm just gonna forward thinking here so you keep these gases in your mind. You'll see that water vapor is actually the most important gas for keeping the planet warm. That's actually the most significant and important greenhouse gas. And carbon dioxide plays a role in there. So maybe in one of the future lessons, we're going to talk about how all of that works. Okay. And you'll see how those things are related together. So the next slide here shows the structure of the atmosphere. So on the left is kilometers, on the right is miles, right? Giving you an idea of the height.
Yep.
See this line here? That orange line, right? Let me erase that so that we don't end up getting. Actually, let me go back. Let me get rid of that marking so we get it clear. So pay attention to that orange line. See how it goes to the left?
Yeah, meanders back and forth. Part? Yeah.
That's temperature.
Okay.
So that orange line shows the temperature with height. That lower layer, the troposphere, that's where weather occurs. So that's what we consider the lower atmosphere. Oftentimes, meteorologists will just for general public, will say atmosphere, atmosphere, atmosphere. We always mean the troposphere.
Right.
We always mean that.
We mean the part of the atmosphere where the weather's occurring, which is
exactly. That's really what we're talking about. We'll just say atmosphere because we're not sure if everyone knows what the troposphere is.
Right.
But when we say, upper atmosphere, we really mean upper troposphere. It's confusing because the upper atmosphere really is not the troposphere.
Yeah.
So
different if you're thinking about like, a rocket trying to leave the Earth, they've got to escape the Earth's atmosphere, but they got to go through all the layers. They're
exactly. Yeah. So sometimes we, it's kind of one of those confusing things. We're like, oh, might not want to say troposphere. That might confuse people. All right. So that line goes to the left. All right. And then see how it goes. So it's getting left, meaning it's getting colder.
Right.
So temperature decreases with height.
That checks out with just human experience. Yeah. You go up on a mountain, it's colder generally.
Exactly. So the sun heats the Earth's surface. And we're going to get to this next time. It doesn't heat the air. It heats the ground. We'll get to that later. So the ground, the lower atmosphere, is the warmest. And so as you go up, the temperature cools with height. And I'm going to give you an example of that in a minute. Now, see where it says tropopause? That's the top of the troposphere where you're going into the next layer. What happens is the temperature now stops cooling.
So that's how we define the tropopause, is when the stops cooling.
That's right. This is how we define every layer, is by temperature.
Okay.
So we define the atmospheric layers by their temperature structure. Troposphere gets colder. It pauses. Now it starts getting warmer. That's the stratosphere. Gets colder. That's the mesosphere. Starts getting hotter again. That's the thermosphere. So follow the way that line is, right? Going to the left, see the temperature down here? Getting colder, getting warmer, getting colder, getting warmer.
Now, at some point you get higher, though, and it get into space and it's colder. So that orange line, does it eventually swing back and is at another layer?
So sort of. So this is where the definition of temperature comes in. All right, so if you follow the layers, you go to the left, you end up in the lower atmosphere, the temperature is cooling with height. You go up, now it's warming, getting cooler, getting warmer. But as you said, well, what happens in space? So this is all about the definition of temperature. So temperature is the speed of air molecules, right? It's not, we have an idea of what temperature is like, right?
Yeah, we think it's heat like given off or whatever.
Yeah, exactly.
Right? Yeah.
We know what 70 degrees feels like. We know what 30 degrees feels like and all of that. But once you get to a point where you're at the higher up, temperature kind of loses its definition. It's not how it feels on your skin. Really, we're recording energy and how fast air molecules are moving. And in the top of the atmosphere, they're moving super fast because they're excited by these particles coming in from the sun. So even though if you look at what we're showing here as a measured temperature of 60 Celsius, like we're really, hundreds boiling, right?
Right.
You would freeze to death.
Yeah.
Even though it's near boiling temperatures.
So it's just looking at that strict definition of temperature, kind of like from a physics standpoint.
That's right. Yep. So we're absolutely not, we're not thinking of temperature as how does it feel once we get out of the lower atmosphere. We're looking at it in terms of the speed of air molecules. All right, so let's just take a closer look at the lower atmosphere. So troposphere, temperature cools with height. Then we get warmer through the stratosphere. So the question is, why is it warm in the stratosphere? Yeah, we'll get to that in a second. But let me give you a little idea here. So let's just say we have a mountain, right? Let's say that mountain is, say, 1,000 feet here, 2,000 feet here. So what are we looking at? Maybe what do we get for 1,000 feet? We're at like 300 meters.
Yeah, that's close enough.
Yeah, so we get about 300 meters and we get about 900 meters, right? So for every 1,000 feet you go up, the temperature cools about 5 degrees.
Right. Yeah.
Called the lapse rate.
So yeah, right? As you go, there's a rate at which when you ascend higher into the atmosphere, whether you're going up a mountain or in a hot air balloon, the rate at which the cooling takes place with elevation.
Yep, about 5 Fahrenheit for every 1,000 feet, or about 1 degree Celsius for every 100 meters. So if you're going hiking,
is that 100 meters or that's 300 meters?
Well, about a Celsius every
1 Celsius. Meters. I got it. Okay, yeah.
Yep. So if you're down here and it's 50 degrees, that means you're going to be 45 here and 40 there. Right. So about 7 Celsius and then about 4 Celsius at the top.
I mean, this is fundamentally why mountains get snow, and that's where the ski resorts are.
Yep. You're cooling with height as you go up through the troposphere. Makes sense?
Yeah, totally.
Pretty straightforward. Now there are times, and we'll get to this at another point, where you could actually warm with height for a short distance, and that's called an inversion, a temperature inversion.
Yes.
And that plays a significant role in like precipitation types and many other things. Like if you have warm air above the ground, say if snow falls into warm air, it will melt. And then it may refreeze into colder air and become sleet.
Okay.
Right? So you'll see that later on, how you could actually get these little thin warm layers even in the troposphere.
Right. Yeah.
All right. So why is the stratosphere warm? Because of the ozone layer. Right. So the ozone layer, which protects us from ultraviolet radiation, is contained within the stratosphere. Right. And this is what you were asking about before about like, do the gases become like layered?
Right.
And ozone is at that right weight mass where it settles in around 20-30 kilometers. Right? Stratified, right? Mm-hmm. So it's now the gases can actually by weight. So the troposphere is nice and well mixed, right? The stratosphere, not so much. And the reaction of ultraviolet radiation with ozone gives off heat. So you release heat in the ozone layer. Now you have all this energy coming in from the sun. So we'll just say it's UV. And then the ozone layer is taking out some of that ultraviolet radiation. So there's UVA, UVB, and UVC. You never hear of UVC, right?
Yeah, it's not
you always hear of
bottle.
Yeah, you never hear of it, right? You never, it's like, you always hear, oh, UVA and UVB protection. But if we had a scale like this, UVA, UVB, and UVC, the ozone layer removes like all of that. It lets in about, I think it's 10% of the UVB, and then all of the UVA.
Yeah.
So UVA is what usually tans you, UVB burns you. And all right, folks, don't get scared here. UVC made it through, it would kill all life on the planet.
Really? And the only thing keeping it from doing that is the composition and thickness and density, I suppose, of the ozone in these.
That's right. It would sterilize the entire planet if UVC got in.
Well, let's keep the ozone right where it is, please.
Let's keep the ozone. And that begs the question of what about the ozone hole, okay? Which the ozone hole opens over the Antarctic in the Antarctic spring for about 2-3 weeks, and is not a hole. It's a thinned out area.
So it lets in more of the UVB. Yeah.
It lets in a little bit more UVB. No UVC comes in and never will. So I don't want to scare anybody here. We have an ozone layer. No UVC is ever going to come in. But this is just to show you how fragile and amazing the atmosphere is. That if the ozone layer wasn't there, UVC would sterilize the planet. And that's a scary thought, but it's also an amazing and awesome thing to think about.
Does the ozone layer get replenished? Are there processes that that destroy it but also create it? Chemical process.
Dead on. It's a constant cycle of this UV comes in, it destroys ozone, but then that energy actually recreates it.
Right.
It combines O with O3, and that high energy radiation recombines it to make O3 again. So it's like this constant cycle.
Right. It's breaking down O3 particles, but it's also combining them together. Well, it works really nicely. It's good.
Yes, we want to keep it that way. Yeah. It's not going anywhere.
And is the troposphere, not going anywhere. Getting to the troposphere, Ben, is it so mixed just because that's where the weather's at and the wind, and you've got just so much dynamic motion in the troposphere that the gases are blended and mixed and not stratified, versus the stratosphere is calmer?
Yeah, you have convection, right? You have air that's able to rise. Think about a hot air balloon, right? Like you're filling it up with that hot air, and that hot air is able to rise. The balloon's able to go up. And that type of mixing motion is pretty uniform through the troposphere, but not in the stratosphere.
Right.
That's where we have warming with height. So now you have the opposite. It's getting warmer with height. You really don't have that mixing. And again, that heat release is due to the ozone layer.
Okay. Got it.
Completely.
Yeah.
Okay. We're going to switch gears a little bit here to optics. And you might ask, well, why this? All right, and you'll see in a minute, and this is going to be important for other things later on too. So we all know the first one. When light hits something and it's returned to you, we call it reflection.
Mirror there.
Now we're going to use this is going to sound funny, but I love teaching people about radiation. radiation is big in meteorology, and we talk about it all the time. And that word, it's a scary word, right? Radiation.
Yeah, sounds bad for
Whenever
you.
you say radiation, it's
Think
cancer.
cancer, right? Yeah. Death.
Light
Yeah.
is radiation. We're surrounded by it. It's everywhere.
Because it's just
There's different types of
energy
radiation.
energy at a certain wavelength.
Precisely, and that's going to be the next topic, and it's an important one. So light hits something, bounces off of it. Any radiation that strikes something and bounces off of it, we call it reflection. Right? And this goes for any type of radiation. If there's a microwave wave, hits something, bounces off of it, reflection. The next one, you ever play that game? Maybe, I don't know, maybe I'm the only one, where you throw like these like glow sticks into like a swimming pool, and then you gotta dive down and go get them. Or
yeah, not glow sticks, but yeah, just to throw things in the pool for my kids to go get.
Yeah, like some kind of, maybe they're colored, whatever.
Yeah.
And when you look in the pool, looks like that stick is there, but it's really, it looks like it's here, but it's really there.
Yeah.
Because as light changes from air to water, it bends. It's called refraction.
Oh, the middle diagram made me think of like putting a pencil in a glass half full of water. It looks like the pencil's bent. Have you heard of that?
That's refraction.
Okay, yeah, got it.
100%. So if you have this half submerged and you look, it's going to look distorted, because when radiation changes medium, meaning air to water or water to air, the light or the radiation, same thing, is bent.
Okay.
So now the next one is called scattering. So air molecules can scatter radiation. Think of it like a filter, like it's breaking the radiation oftentimes into different wavelengths. So it depends upon the type of radiation and the type of particle. So in this case, we're talking about gases like in the atmosphere.
Mm-hmm.
So if you have radiation striking an air molecule, sometimes those air molecules will split the radiation into different wavelengths. It's going to be important for the next topic, but also in future things. So keep these in the back of your mind.
Is this like a rainbow? Is this the same as a rainbow, kind of?
That's where we're going. We're not going to talk about rainbows yet, but that's one of them.
Okay.
Rainbows involve almost all of these, but that's coming.
Okay.
All right, so here's the sun. All right, this is an X-ray image of the sun. What we're actually looking at is the sun's atmosphere, called the corona. And it's actually hotter than the surface of the sun. It's so hot that it emits X-rays. Kind of like when you go to the doctor, you get an image of your teeth, or you break a bone, you get an X-ray. We're actually looking at X-rays coming from the sun. We're looking at the sun's atmosphere. The sun emits all kinds of radiation: X-rays, gamma rays, visible light, microwaves, radio waves, ultraviolet, a whole bunch of different types of radiation. And we call it the electromagnetic spectrum.
Okay.
So all of the energy that comes from the sun, all light, all radiation, carries with it an electric and magnetic field. Now, you look closely, so it gives you some examples of the type of waves that various things emit here, that we deal with.
Yeah.
So shorter wavelengths are in this direction, and longer wavelengths in that direction. Right here, visible light, that's what we see with our eyes.
Pretty narrow band. Okay. We're not seeing
that very narrow, very narrow band right there. Now, from roughly here onward, that's the bad stuff. It's called ionizing radiation. So that's a type of radiation that could break down chemical bonds. It could mutate DNA. So that's when we're at the UVC level and beyond. X-rays, gamma rays, these things are not coming into the atmosphere, but that's the dangerous stuff. Now notice microwaves, radio waves, they're on the good side.
Mm-hmm.
They're on the non-ionizing part. And a lot of times, and microwaves play a role in meteorology for radar and satellite. So that's why we need to introduce this now and some other things. But let me just talk briefly about this. So people say you're scared of your microwave oven, right? Which, I know some folks out there, you're irradiating your food.
Right.
You're not. You're not. So the microwave oven, it's emitting these microwaves and at a lot of power and at a higher frequency. So these microwaves are in there, and the electric field in the microwave is causing water molecules to rotate. Water molecules have almost like a north and south pole, like a plus and minus. And as the microwaves oscillate back and forth, the water molecules in the food are going like this.
Right.
They're trying to reorient to the microwave's north and south pole. So they're kind of going crazy, and that causes heat.
Right. Just the movement causes frictional heat.
It causes, yeah, exactly. Guess how many times that those water molecules are trying to flip up and down?
Gosh, like in a minute setting on the microwave, I imagine they're moving like thousands of times, maybe.
2.5 billion times per second.
Wow.
So
that's insane.
It's absolutely incredible. So the idea here is, there's bad radiation and there's radiation that's not bad. Microwaves are not one of them, but just to show you that, and these become important later on in meteorology and have a lot of uses within the field. So we're gonna revisit that. But let's focus here for a moment. All right, so infrared, ultraviolet. In the middle is the light we can see. And the best way to remember this is the first color is red, right? R. I got a big fat pen here. Let me reduce it down a little bit so that you can kind of see it. So R is red, orange, Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. So what are the wavelengths that are close to red? Infrared. It means near red. So infrared we feel as heat. So it's basically saying that those wavelengths are close to red.
Yeah.
And then violet, it means beyond violet, after violet.
Violet on steroids.
Exactly, right? So yeah. That's what it all means. All right, now let's go back to scattering. Remember the visible light, okay? Let me zoom back out here. Now, as light enters the atmosphere, it more effectively scatters violet and blue. So as visible radiation, visible light is coming into the atmosphere, the gases in the atmosphere, nitrogen, oxygen, they split out the blue and violet the most. And human eyes are more sensitive to those shorter wavelengths of blue and violet. And we are especially sensitive to blue. So that's why the sky looks blue. So it's not a reflection.
Yeah.
It's that the atmosphere scatters these shorter wavelengths more effectively than the longer ones.
Right. So it's dominating. Yeah.
It's dominating.
Right.
Now, that means that other animals are not seeing the sky as blue because they don't have the same eyes as us.
Right. Different.
So your cat, your dog, they're seeing the sky as like a grayish blue color. And a lot of insects and birds actually see a much richer, deeper blue, and they actually can see a little bit of the ultraviolet. So the sky might appear like a deep blue purple to them. And there are some, I think that there's some sea life that the sky is almost blank to them. It looks kind of washed out like a light whitish gray color. So kind of one of these things we have to keep in mind that not everyone is seeing the sky as the same color in terms of like all of the, our furry friends are not seeing the same blue as us. And it probably doesn't occur to a lot of people that that's occurring, right?
Yeah.
So
so
so now, okay, so if the sun is directly above your head, you're seeing the blue colors. If the light is coming in at an angle like it is in this picture, what happens is the blues and the violets get scattered away, like lost at the top of the atmosphere. So what's left? Orange and red. So that's why at sunrise and sunset, when the solar beam, the angle is coming in low, you're left with seeing oranges and reds because the blues and the violets have been scattered away. They don't reach your eyes.
Right.
They're scattered away at the top of the atmosphere. So think of it like a filter, like the atmosphere has filtered out, almost like how the ozone layer filters away the UVB and the UVC. Think of it as when the sun is traveling through a longer path through the atmosphere, not only is the UVB and the UVC gone, just the air alone now takes out the blues, it takes out the violets, and by the time it reaches your eyes, the oranges and reds are left over, and that's why the sky looks red and orange at sunrise and sunset. And so
very cool.
Yeah. So it's essentially like it's almost like the atmosphere is a filter, and you can kind of see it in this image here, and even here you basically have like the reflection of the orange sun on this is from the International Space Station.
Wow, it's beautiful.
Yeah. So this is what it's all
it's
about
like a
is
painting almost.
Yeah. What it's all about is just trying to understand these type of processes. So that's a basic overview.
Okay.
And in further episodes of this, we're going to expand on a lot of these topics and dig more into, we'll talk about rainbows and how those occur, and they involve these things like reflection and refraction and scattering and stuff like that. And you can see like why we get certain colors. And, I look at that stuff as being, is it the most exciting topic in the world? No. But
right.
It's cool.
Yeah. And I think, ultimately, I think it's all basic physical science as applied to the Earth's atmosphere that's going to help us learn, why does the wind blow hard, and why do we get, cold winter storms on the East Coast, and why do we have warm weather in the tropics? And I think that'll help us understand everything. So this is a great introduction.
Yep. All of this is going to be related. We'll have to circle back to this, and we're going to talk about, infrared radiation and how it heats up the Earth. We're going to talk about how we use microwaves to detect precipitation. That's radar, right? There's lots of things that we do with what a lot of people think of as the scary thing called radiation, and we have to kind of demystify it.
Yeah, it's really just energy.
It's energy.
Energy, right?
Yeah. There's parts of it that we don't want to reach the Earth's surface ever, right?
Right.
But there's a lot of it that is. It's not a cancer thing. How a lot of folks may read it.
Right.
It's an important part of like the cycle in the atmosphere, and also tools that we use to help us forecast, help us detect precipitation. So this will follow on from there.
Perfect. Well, this has been a great first episode, Ben. Viewers, just, I know this can feel like a little deep science-wise, but like just really try to wrap your head around this. And Ben's doing a nice job of kind of like laying the groundwork, trying to like relate some of these concepts to things in our everyday lives. And then this will help us build that foundation and help us understand weather and how it affects us, and just the variables that go into weather and all the different things we see associated with weather in our atmosphere. This has been a great first episode. Please make sure you like this one. Leave comments if you'd like to. We'll check those out, and then we will get another episode out to you as soon as we can. Thanks so much, folks.